Good afternoon, everyone. Why don't we get started? Thank you all for being here. It's really great to see so many people coming out this afternoon for this really terrific talk on meeting the climate change challenge. My name is Rick Locke, and I'm a professor here at Brown in political science and international public affairs, and I also currently serve as provost. And I'm pleased to join President Chris Paxson and by our leaders in the co-sponsoring organization. So Ed Steinfeld from Watson, Amanda Lynch from IBIS, and Dr. Philip Duffy, the president of the Woods Hole Research Center, and we'll say more about that later, who have come together to host this really terrific event. Now, what we try to do here at Brown, at IBIS, at Watson, and throughout the university is to really bring together faculty and students and staff to work on some of the world's most critical challenges. And climate change is arguably one of, if not the most challenging issue that faces us today. And that's why it's so important to bring together policymakers and scholars and practitioners together. And our featured speaker today has devoted much of his professional career to undertaking and translating cutting-edge science to effect meaningful change. Now, John Holdren served for 8 years as President Barack Obama's top aide on science and technology issues and was the longest-serving director of the White House Office of Science and Technology Policy. Now, his responsibilities were quite broad. He was responsible in this capacity for advising the president on all science and technology issues bearing on the president's far-reaching agenda. So economic growth, job creation, biomedicine, public health, energy, climate change, and much more. And I had met John a couple times, once when I was a faculty member at MIT and we tried to recruit him to MIT. Unfortunately, he chose to go to another university up the road. And then later on, when he was serving as the director of the Office of Science, Technology, and Policy, both Ed Steinfeld and I were involved in our last year at MIT. We're involved in this very great project called Production in the Innovation Economy. How should we think about manufacturing and those kinds of jobs in an economy shaped by innovation? And so we went to Washington. We did all these, had these meetings with different congressional staff and different congressional leaders, and then had a really terrific meeting with John and his staff, where it was really obvious that he knew the details of the issue, that he really cared passionately about what we were trying to do and why this was important for the nation. And it was incredibly refreshing to have a public servant who not only knew the science and knew the policy, but passionately cared. Now, I'm not sure if John will do this, but I'm sure he has much to say about what has happened to the Office of Science, Technology, Policy over the last year, and how concerned we should be. But I'll leave him to maybe talk about that. Prior to joining the Obama administration, John was the CEO of the Woods Hole Research Center, now one of the sponsoring organizations of this event, and an organization that we have entered into a memorandum of understanding to do joint research on issues around climate change, which is really, really terrific. He rejoined the Woods Hole Research Center in 2017. He had been the president of that. He was in the Obama administration. He has served as a professor in a variety of major universities. And he continues now to serve in a voluntary role at Woods Hole Research Center. Now, for those of you who don't know it, Woods Hole Research Center is really this kind of gem of a research center that really makes has a major impact on a variety of different issues, but especially on issues related to climate change. It's doing exceptional work, and we were very fortunate a couple summers ago when Phil Duffy, also George had come and talked to us about how could we partner between Brown and Woods Hole Research Center, and it's been really terrific to do that. I know the work has already started. There's been some very cool work being done already in Brazil, and I hope to see much more of it in the months and years to come. Now, the aim of this agreement, this partnership between Brown and the Woods Hole Research Center, is really to bring together students and faculty and researchers to engage in policy-relevant research, to create pathways that translates research into impact. And ultimately, what we want to do is not only understand the incredible challenges that we face as a result of environmental change, but try to work on solutions. What can we do? As Stephen Porter reminds us here at Brown, the window of opportunity is very limited. What can we do within this window of opportunity so that we can really make a difference? And John Holdren is a linchpin to this solution. In addition to his significant public service, he is, as I think everyone knows, a renowned scholar. He did earn his bachelor's and master's degree at MIT and then got his PhD at Stanford. He was a professor at Stanford in aerospace engineering and theoretical plasma physics, but today he's a professor at the Kennedy School, continuing his work on science, technology, policy. John, it's a terrific honor to have you here at Brown. Please join me in welcoming John Holdren to the podium. Thanks so much.
Well, thank you very much for that generous introduction and also for saying nice things about one of my favorite institutions, the Woods Hole Research Center. It's great that the Woods Hole Research Center and Brown have entered into this partnership. I think that's wonderful. I'm honored to be here, honored by the presence of the president of Brown University, Christina Paxson, sitting in the front row, by a number of folks I've known for many years. Professor Jim Gates, somewhere here, is going to have to leave and teach, but he was one of my colleagues on President Obama's Council of Advisors on Science and Technology for many years. And of course, my friend and colleague, Dr. Phil Duffy, the president and director of the Woods Hole Research Center, is here along with a delegation from the center. So it's just a great moment for me to talk about meeting the climate change challenge, what we know and what we should do. I'm going to cover a lot of ground here. Some of these slides will go by perhaps a little quickly. The consolation for the folks in the audience who care about the details is we will post this presentation on the Woods Hole Research Center website. For all I know, it may also be posted here at Brown. But in any case, you will be able to find it on the Woods Hole Research Center website if you want to take a longer look at some of these slides. So I start with a few basics, namely, what really is the essence of what is often called not just the climate change challenge, but the energy climate challenge. And the essence is that without energy, there's no economy. Without climate, there's no environment. And without economy and environment, there's no material well-being, there's no civil society, there's no personal or national security. And the real essence of the challenge is that for a very long time, the world has been getting most of the energy its economies need in ways that are now seriously disrupting the climate that its environment needs. That really is at the heart of the matter. Second basic has to do with terminology. Global warming, I've been arguing for decades now without much success, is a misnomer. The term global warming implies something that's uniform across the planet, that's mainly about temperature, that's gradual and quite possibly benign. What could be wrong with a little bit of warming? I think that term has actually confused a lot of people. What's actually happening is highly non-uniform. It's not just about temperature. It is rapid compared to the capacities both of ecosystems and societal systems to adjust. And it's harmful for most places and most times, and getting more so. That is, some benefits from a bit of warming in some places for some period of time, but as it proceeds, it becomes more uniformly negative for every place in the world and everybody in the world. A more descriptive term would be global climate disruption. The changes are not just about temperature. Important to understand the distinction between climate and weather. Climate really means the patterns of weather, the averages, the extremes, the timing, the spatial patterns of, yeah, hot and cold, that's part of it, but also cloudy and clear, humid and dry, drizzles, downpours and hail, snowfall, snowpack and snowmelt, breezes, blizzards, tornadoes, typhoons. And climate change means disruption of the pattern, not just increase in temperature, but disruption of the pattern. The global average temperature, which is what climate scientists use to characterize how far along we are in the process of human-caused climate disruption, is just an index of the state of the global climate system as expressed in all of those patterns. And just as your body temperature is an index of the state of a very complex underlying system, the global average surface temperature of the planet is an index of the state of a very complex underlying system, and a change of a couple of degrees is a big deal. If your body temperature goes up 2 degrees Celsius, 3.6 degrees Fahrenheit, you know it's telling you something is amiss in the system. And the same thing is true of the Earth's climate. By coincidence, 2 degrees C is a big deal for either one, your body temperature or the planet's temperature. This is what led Al Gore, Vice President Al Gore, to say decades ago now, the Earth has a fever. When the average of any of these weather variables changes, the extremes change much more. And that principle holds for any normally distributed climate variable. A modest change in the average entails big changes in the tails. And you see this laid out in schematic form here. You move the distribution, in this case of temperature, a little bit toward the warmer end. And look what happens at the tail, a huge increase in the amount of hot and extremely hot weather, out of proportion to the change in the average. We'll see more about this shortly. Changes both in averages and extremes matter because climate governs, and therefore altering climate affects the availability of water, the productivity of farms, forests, and fisheries, the prevalence of oppressive heat and humidity, the formation and dispersion of air pollutants, the geography of disease, what pathogens and vectors can live in what abundance at what times of the year, in what places, the damages that we have to expect from storms, floods, droughts, and wildfires, the property losses we have to expect from sea level rise, and the expenditures on engineered environments, how much of the Earth's surface we need to air condition in order for people to be comfortable and be able to work, how much we have to spend on dams and dikes, and so on, and the distribution and abundance of species of all kinds, the species that we need, the species that we love, and the species that we hate, all influenced in their abundance and distribution by the climate. Now let me just outline very quickly where I'm going in this presentation from here. Start with what we know beyond a reasonable doubt about the pace, character, and causes of climate change, the ongoing impacts on people and ecosystems, the question about the future, what do we expect, scientific best estimates of where it's going under specified future scenarios of emissions of the substances that are changing the climate, and beyond the scientific best estimates, things that we're not quite so sure about, but what else could happen where the timing, the probability, the magnitude is still uncertain, hard to quantify, but possibilities that have to be reckoned with. Finally, what we can do, reducing emissions, adapting to unavoidable change. We can't stop climate change in its tracks. It's already changing. It will change more before we can bring it to a halt. The need for and the current lack of federal leadership in this domain. And finally, what states, cities, businesses, universities, I couldn't fit it all in, non-governmental organizations, and citizens can do. So start with what we know, and my favorite quote from Daniel Patrick Moynihan: everyone is entitled to his own opinion, but not his own facts. We know that Earth has been warming more or less steadily for the last 100+ years as the increasing forcing, this is a term used in climate science, it means literally how hard are you pushing on the climate with one influence or another? Those influences could be natural forcings, they can be human forcings, but the human forcing has become dominant, particularly in the last 70 years. Every decade since the 60s has been warmer than the last. 2016, the hottest year since 1880. 1880 is the point at which the major U.S. organizations that keep track of these things decided that worldwide thermometer measurements are dense enough to meaningfully calculate a global average surface temperature. The British authorities who do this think it goes back to 1850, so you'll see some different records of this sort, but this is what is sometimes called the instrumental record. Earlier, we have to rely on what are called proxy indicators of climate change, things like isotopic composition of gases, gas bubbles trapped in ice cores, fossil corals, fossil pollens, tree rings, and so on. But these are the direct measurements using thermometers of what the Earth's temperature has done. You see that besides 2016 being the hottest year in this record since 1880, 2017 just finished was the second hottest, 2015 the third, 2014 the fourth. 17 out of the 18 hottest years in the record all occurred from 2001 to 2017. Statisticians among you can figure out what the odds are that that would happen by accident in a world that was not being systematically pushed in the warmer direction by something. We'll talk in a minute about by what. I mentioned that it's not uniform. This is a picture of 2016's warming versus a baseline of the 51 to 1980 average in degrees C. The overall average for the Earth in that period is about 1 degree C. That's the 0.98 over on the right. And you see that the Arctic, the West Antarctic Peninsula, and the mid-continents, particularly the northern hemisphere mid-continents, are warming much faster than the global average. And that has significance in many respects when you have these uneven influences, this uneven heating. It influences circulation patterns, the circulation of the atmosphere, the circulation of the ocean, and that is an enormous influence on local and regional weather, which is changing along with these global indexes. Arctic sea ice extent, not surprisingly, given how much faster the Arctic has been warming than the global average, has been shrinking rapidly. This graph shows over the era of satellite imagery, which gives us accurate measurements of how much of the Arctic Ocean is covered with sea ice. The maximum is in March, the minimum is in September. Both have been shrinking. The sea ice maximum in March has been shrinking. The sea ice minimum in September, the end of the summer, has been shrinking even faster. And what you see in the inset is the difference between the rate of temperature increase in the Arctic, the black curve, and the global mean increase in temperature. And you see this point about how much faster the Arctic is warming. Antarctic sea ice is in trouble too. Not long ago, an iceberg about the size of Rhode Island, in fact, I think bigger than Rhode Island, maybe the size of Maryland, broke off of Antarctica. Of course, when sea ice shrinks and when sea ice breaks away as icebergs, this does not change sea level. But what it does do, if you lose sea ice in Antarctica, it allows the land ice to flow more rapidly to the sea, and that influences sea level. Those floating ice shelves in Antarctica are holding back the land ice, which, if it reaches the ocean, raises sea level. Glaciers worldwide have been shrinking for decades. We could spend a whole hour with the dramatic pictures of glaciers all over the world, the Himalayas, the Andes, Alaska, elsewhere, shrinking. This is a glacier in Alaska, the Muir Glacier, picture taken from the same vantage point in 1941, August 41, again in August 2004. Stunning retreat of the glacier. The Greenland ice sheet has been losing mass at rates fluctuating between 100 and 500 billion tons per year. Most recently, We measure this with the GRACE satellites that use gravitational anomalies to see how much ice is there. We now know, we didn't know this 10 years ago, but we now know that the Antarctic ice sheet is likewise losing mass at rates that are now, when you run a best fit through there, ranging and declining from 50 billion tons a year around 2005 to 200 billion tons a year in 2015. Not shockingly, the pace of sea level rise is increasing. It's not just that sea level is increasing, it's increasing faster and faster. What you see here is the trend from 2010 to 2016 is twice as great as the trend from 92 to 2016, and that's twice as great as the 20th century average. So the recent rate of sea level rise is 4 times as great as the 20th century average, and those increases result, as noted here, not only from the additions of ice from the glaciers and from the Antarctic and Greenland ice sheet, they result as well from thermal expansion of the ocean. The ocean warms in a warming world, and warm water gets less dense. Sea level rise goes up for that reason, and also groundwater depletion. When you pump groundwater faster than it is replenished, and ultimately it runs off in the rivers, that contributes as well to sea level rise. So what we know about the causes. I like this quote from Neil deGrasse Tyson: "Science is true whether or not you believe in it." What we know is that the growth of world population and prosperity in per capita terms on the average between 1850 and 2015 led to a more than 20-fold increase in global energy use, most of that driven by fossil fuels. The brown at the bottom is largely traditional biomass energy forms: fuel wood, charcoal, crop waste, and dung. But the great bulk of the increase from 1850 to 1950 was coal, the gray band. Great bulk of the increase from 1950 up to roughly the present was oil. Natural gas coming in there importantly from 1970 or so on. And then you see these little contributions from nuclear and hydro and other renewables. For all one hears about those, quote, clean energy sources, they together add up to a bit less than 20% of the world's primary energy. Coal, oil, and natural gas still provide, in today's world, about 80% of total energy, 2/3 of all electricity generation, and using technologies that release all of the carbon contained in those carbon-based fuels into the atmosphere as carbon dioxide. And so, not shockingly, civilization's carbon dioxide emissions tracked the rise of fossil fuel use, and also deforestation and other land use changes. This contribution from deforestation and land use changes is indicated in brown at the bottom. This is one of the major focuses of the Woods Hole Research Center. George Woodwell, its founding director, was one of the pioneers of pointing out how important land use change is in this business. When you burn fossil fuels, you release not only carbon dioxide to the atmosphere, you release water. Water vapor is a potent greenhouse gas, but it stays in the atmosphere only briefly, so it doesn't accumulate. The carbon dioxide has an enormous lifetime in the atmosphere, and so it does accumulate, and the atmosphere CO2 content grew markedly as a result of this. This is the record of carbon dioxide content of the atmosphere over the millennia. The main diagram here goes back 10,000 years before 2005, based on, again, gas bubbles trapped in ice cores. And you see this stunning rise in atmospheric CO2 gradually, initially from the agricultural revolution. That's the deforestation and land use change. And then around 250 years ago, the Industrial Revolution, a rapid increase in the use of fossil fuels, and you see this stunning break in the curve and this rapid rise that's expanded from 1800 or so in the inset. On the left is the carbon dioxide concentration. On the right is the forcing measured in watts per square meter averaged over the surface of the Earth. Again, how hard that carbon dioxide buildup is pushing on the energy balance of the atmosphere and therefore on the climate. We've not only added carbon dioxide, we've added other heat-trapping gases, the most important ones, methane and nitrous oxide. Those come from energy systems and agriculture. Most recently, we've also been adding chlorofluorocarbons and hydrofluorocarbons from consumer products and industry. You see that the CO2 is the most important. Here the measurement is in forcing, so that these are comparing apples with apples and not apples with oranges. But the methane, the nitrous oxide, and the others are all important, even though much smaller than the carbon dioxide. Now, in terms of what we know, within the measurement uncertainties and the analytical uncertainties, essentially all of the recent observed warming was human-caused. The red arrows point to what has been observed as the increase from 1950 to 2010 in the global average surface air temperature, and the second red arrow is the net human influence when you take into account the so-called well-mixed greenhouse gases, carbon dioxide, methane, nitrous oxide, and the influence of particulate matter, much of which is reflective and tends to cool the Earth, and short-lived greenhouse gases. You see solar variability in volcanoes. Net over this period are essentially zip, and the same for internal variability. Internal variability makes the curves bumpy, but the net warming over this period virtually all caused by humans. There are folks I call wafflers now. They're not quite the same as deniers. They say, yeah, climate is changing. Humans may have something to do with it, but we don't know how much. That is nonsense. We know how much, and the answer is essentially all of it. By the way, most of President Trump's cabinet nominees were asked about climate change in their confirmation hearing, and as if it was a catechism, all of them recited this point. Yes, they were asked about climate change. They all said, yes, climate is changing, and yes, humans may have something to do with it, but we don't know how much. Nonsense. Continuing with causes, humans are clearly the cause. Nature was heading the other way. Natural influences, this is again something in the range of 12,000 years based on climate change proxies, and then instrumental measurements at the very end of this. Natural influences on Earth's climate, principally variations in Earth's orbit and axis of rotation that take place on 20,000, 40,000, and 100,000 year timescales, were in a long-term cooling phase for roughly the last 7,000 years until 250 years ago, when these human influences became dominant. And again, the graph is absolutely striking. What we did, what humans did, is we avoided another ice age. Had we not intervened, maybe in another 10,000 years, under natural influences, we would have been in another ice age. So some people say that's a great thing. I say we overcompensated. So turning to what we know about ongoing impacts on people and ecosystems, not projected impacts, but what we know about what's happening now. This is a favorite issue of mine, although it's depressing. For years, decades, there's been a debate among scientists and climate policy folks about the question of when we cross the threshold of dangerous human interference in the climate system. The reason for that argument is the 1992 United Nations Framework Convention on Climate Change embodied as the goal avoiding dangerous human intervention in the climate system. And so people have been arguing ever since 1992 about whether we have dangerous. In my opinion, and I will support that in a moment, we passed dangerous some time ago. The question is not whether we can avoid dangerous. The question is whether we can avoid catastrophic. Serious harm is already occurring in many different forms. Serious harm is here now. We are seeing around the world variously increases in all of these things: floods, droughts, wildfires, heat waves, coral bleaching, coastal erosion and inundation, the power of the strongest storms, permafrost thawing and subsidence, expanding impacts of pests and pathogens, and altered distribution and abundance of valued species. And all of these phenomena, all of these increases, are plausibly linked to climate change by theory, by models, and by observed fingerprints, meaning the patterns in which these changes are occurring. And most of them are worsening faster than was, until very recently, projected. Let's look at some of these. Heavier downpours leading to more floods. This shows the increase in the amount of precipitation falling in the heaviest 1% of precipitation events in each region between 1958 and 2012 in the United States. Every region except Hawaii, which was dominated by circulation effects rather than what happened with these larger areas, atmospheric circulation effects. This is rather elementary, as it says at the bottom. It's one of the most elementary consequences of a warming world. A warmer atmosphere can hold more water, and if it's holding more water, more can and does come down at one time. And that is leading to the increases, together with some other influences, leading to the influences that are being observed in flooding. 100-year floods are now occurring once a decade or more in many places. 3 500-year floods, that means before we were messing with the system, these were floods that could be expected to occur once in 500 years. 3 500-year floods occurred in Houston in 3 years. Hurricane Harvey brought more than 50 inches of rain over 5 days to parts of Texas in August of last year. The pictures are East Baton Rouge, Los Angeles, before and after the floods of August 2016, up to 20 inches of rain in 3 days. And yet, in what some people regard as a paradoxical phenomenon, in a wetter world overall, many drought-prone regions are getting more prone to drought. How could this be? There are a number of phenomena at work. One is that higher temperatures mean bigger losses to evaporation, drying out the soil. The fact that more of the rain falls in extreme events means more of it is lost to flood runoff and less soaks into the soil. Mountains are getting more rain and less snow. That yields more runoff in winter, and that leaves less for summer and fall when the droughts occur. Earlier spring snowmelt also leaves less runoff for summer. And we are also, through climate change in ways that I've mentioned already, altering atmospheric circulation patterns, and those often also play a role in increases in drought. Drought in the Amazon, this is a particular focus of work at the Woods Hole Research Center. This shows the precipitation index for Brazil in the 2 years, 2015 and 2016. I hope you can all read the scale. The dark magenta is extremely dry, and the red very dry. This is really devastating, and I'll say more about that in a minute. But this, again, these are measurements. This is history. These are not forecasts. These are not computer models. This is what is already happening. Wildfires. This is a plot of how many millions of acres burned annually in U.S. wildfires between 1981 and 2015. The contributing factors, as indicated here, are heat, drought, more dead trees killed by pests, which provide the tinder for these fires, and more lightning in a warming world. This was not understood until a few years ago, that a warming world also produces more lightning, and lightning is the principal igniter of wildfires. It's even more important than human error, people not tending to their campfires or throwing their cigarettes out the window. Lightning is more important than all of that. I just update this with the 2016 and 2017 figures. 2017 nearly matched the earlier record, 10 million acres burned. Now, I don't know what happened to the formatting here, but I'll read you what it's supposed to say. The fire season in the United States is now about 3 months longer than it was 40 years ago. It's an astonishing number. 3 months longer. The average fire is much bigger and hotter than before. Small wildfires burn at 1,400 degrees Fahrenheit. Big ones can burn at 2,000 degrees Fahrenheit or more. And of course, we're getting lots of big ones. That spreads the fire faster, destroys more buildings, produces far greater risks for firefighters. In Alaska, even the tundra has been burning. Formerly in Alaska, wildfires only afflicted the forested regions. Now the tundra has been burning. And the smoke from today's big wildfires can carry health-harming fine particulates thousands of miles. And here's a picture of that. Smoke spreading nationwide from the September 2017 wildfires in the northwestern United States. Fine particulate matter, PM 2.5, average diameter 2.5 microns or less, an extreme health hazard. And you can see it spreads clear across the United States. Another big one, a sleeper really, I think this was not terribly well understood 15 years ago. It's well understood now. Huge increases in heat waves. This comes from the phenomenon I showed you before schematically with the Gaussian distribution. Slide it a little bit to the warm end and you get a huge increase in the extremes. These now are actual data. Except for the black line, which is a normal distribution for the period 1951 to 61. The actual distribution for 51 to 61 is in red, and you see the normal distribution fits it very well. Still fits pretty well up to 71 to 81, and then it starts sliding to the right. And if you look out, this is 3 standard deviations over on the right. What happens at 3 standard deviations, what was something like a 1 in 700 year event now becomes 50 to 100 times more probable. These distributions are showing the portion of northern hemisphere land that experiences in any given summer a 3 sigma warm summer as a whole. And that portion went up from 1/10 to 2/10% in the period 51 to 80 to 10% in 2001-2011. 50 to 100-fold increase in the extreme events. This is absolutely stunning, and people have not generally taken this on board. Again, they're looking at the average temperature. Oh, what's 1 degree C? Well, it is huge when it comes to the impact on the extremes. More northern hemisphere winter extremes associated with a very interesting phenomenon. You've heard about the polar vortex, I suspect. It gets publicity every time there's an extreme winter cold spell, and Senator Inhofe throws a snowball in the Senate and says climate change is a hoax. What is clearly happening here, there have been some arguments about the details, but this is increasingly robust. Rapid warming in the Arctic reduces the temperature difference between the Arctic and the mid-latitudes. That temperature difference is what drives the polar vortex. Temperature difference goes down, the polar vortex weakens, the jet stream that bounds it becomes wavier, and it circulates, it moves more slowly, and what you get is a wavy jet stream and alternating slow-moving southward incursions of cold air and northward incursions of warm air. So you get record warm temperatures for a while and then record cold temperatures for a while. And in the northeastern United States, you have this phenomenon where cold Arctic air, when one of these downward lobes brings cold air from the Arctic to the northeast, that collides with moisture-laden air over an Atlantic Ocean that has been warmed by the warmer atmosphere overall, and you get extreme snowfall. Coral bleaching, the oceans are under direct threat. Bleaching of coral, partly, in fact, probably largely due to the warming of the surface layer of the ocean, although also perhaps influenced to some extent by acidification. 2017, the strongest global coral bleaching event ever observed. Compounded by ocean acidification, 1/4 to 1/3 of the CO2 added to the atmosphere goes into the oceans. That dissolved CO2 forms weak carbonic acids, very simple chemistry, but quite complicated in what happens then. And what is particularly difficult about it is that this condition of lowered pH complicates the lives of all the organisms that make their skeletons or their shells out of calcium carbonate. And that includes clams, shrimp, lobsters, oysters, and perhaps most importantly, a lot of the plankton that sit, particularly zooplankton, that sit near the bottom of the food chain and on which ocean food webs are heavily dependent. You look at what has happened to the coral reefs in Florida in particular. This is quite stunning. The coral reefs in Florida devastated by multiple stresses, the most important of which are warming water and acidification. Less than 10% of what was the reef system in the Florida Keys is now covered by living coral. 90% of it is gone, is dead. The red circles show percentage decline since 1996. This is one of the slides that repays a closer look. I can't really tell you all about it in the time available, but this is immensely consequential economically for Florida and the Florida Keys. Thawing and subsiding permafrost, pictures from Russia and from Fairbanks, Alaska, giving examples of what thawing permafrost does to buildings and infrastructure, in this case roads that are sitting on top of permafrost when it thaws. Rising sea leading to coastal inundation. This is what is also called nuisance flooding, where high tides and a rising sea level combine to flood the streets in coastal communities. And this again is quite stunning when you look at it in detail. The blue bars at the top are average number of flooding events per year in the period 50 to 69. The red is 70 to 89. The green is 90 to 2009. And look at 2010 to 2015, average number of flood events per year. The blue bar, it is stunning. In every one of these locations, the incidence of this flooding is increasing rapidly. Rising sea levels also lead to coastal erosion. This is a picture from one of my local newspapers, the Cape Cod Times, showing coastal erosion taking place on Cape Cod, 33 acres a year being lost to inundation and coastal erosion. Stronger tropical storms. It is absolutely striking that the largest, strongest tropical storms, typically called hurricanes in the western Atlantic and Caribbean, typically called typhoons in much of the rest of the world. In all of these basins, the largest and or the strongest have taken place since 2012. Again, if you're a statistician, you could have fun trying to figure out how likely this is if something wasn't pushing very strongly on the system. Growing harm from pest outbreaks. Pine bark beetles get a longer breeding season. They get one extra generation courtesy of global warming, and they have been devastating trees that are already weakened by heat and drought in California, Colorado, and Alaska. Millions of acres of spruce and pines have been destroyed. All of this red-brown is dead trees. And that has not only lost economic value and lost tourism and lost lumber revenue, but it's more tinder for wildfires. Increased vector-borne disease, a bunch of numbers here about Lyme disease, West Nile virus. Dengue is also an issue. Malaria is an issue. These formerly confined hazards to human health, these direct hazards to human health, have been expanding. Impacts on valued species. Here are a couple of titles from recent scientific publications about impacts on fisheries, one in the east, one in the west. Cod in Maine, salmon in the Pacific coast. Other valued species in the far north, in the Arctic, where again climate is changing so rapidly. And again, the inset is another picture of the minimum annual sea ice extent, the mid-September sea ice extent. And this picture on the left is walruses by the thousands hauled up on the shore where there is nothing to eat. Why are they on the shore? Because the ice from which they used to hunt and find their food is gone. Whales, seals, and polar bears are also all being affected, and these are the basis of subsistence hunting for the indigenous peoples that live in the far north. What's coming? The future of climate change and its impacts. Again, I've been talking about what's already happening. Talking about the future is harder. This is another quote I like. It's variously attributed to Yogi Berra and the physicist Niels Bohr. Prediction is difficult, especially about the future. It's inherently more controversial, inherently more uncertainty than things we've already observed. But you take a look at the IPCC, the Intergovernmental Panel on Climate Change Scenarios, for everything from very low emissions to very high emissions going through the end of this century. And what you find is that global average temperature continues to increase under all plausible scenarios, but it increases a lot more under the high emissions scenarios. And what is also very striking, we know that the last time the temperature was 2 degrees Celsius above the 1900 level was 130,000 years ago. 130,000 years before the present, and at that time, sea level was 4 to 6 meters higher than it is today. That's the equilibrium. Nobody knows for sure how long it takes the ice and the ocean to come to equilibrium with the alterations we're imposing on the climate. Some people say it'll take 2,000 years, which is a blink of an eye in geologic time, quite a long time for human society. Other people say there may be mechanisms that can cause this to happen much more quickly. The last time, by the way, the temperature was 3 degrees C above the 1900 level was 30 million years ago, and sea level was 20 to 30 meters higher than today. Key point is that the momentum in the climate system means that temperature continues to go up even after atmospheric conditions stabilize, and sea level continues to go up even after the temperature stabilizes. And so you have these huge time lags, which, by the way, is a very great challenge for policy, because we're not experiencing at any given time the full consequences of what we've already done, which causes policymakers to understate how serious the problem is. Continuing with scientific best estimates under specified future emissions, we know with rather high confidence that heat extremes are going to multiply. Here are a bunch of titles, again, just of recent scientific publications about what we expect to happen with heat extremes, which, as you saw from the earlier pictures of these Gaussian distributions moving to the right, there's already been a huge increase in heat extremes, but it's going to get worse. This is a very telling slide, which you'll probably have to look at your leisure because I'm running out of time. But there was a heat wave in southwestern Europe, southern France, Spain, and Italy that in 2003 killed between 35,000 and 70,000 people. Time it occurred, it was judged to be, would have been a 1 in 500 year event if we hadn't been fiddling with the climate already. Time it happened, it was about a 1 in 200 year event. By the 2040s, under continuation of business as usual emissions, it would be a 1 in 2 year event. And by the 2070s, this would be an unusually cold summer in the region. A summer that in 2003 killed between 35,000 and 70,000 people from heat stroke, heat stress, and the like. Same for the United States. It's hard to read the bottom scale here. I apologize for that, but what the bottom scale shows, this is the increase in total heat wave days between the period, the baseline here is 1970 to 2000, and the factor increase in total heat wave days from that baseline to the middle of the century we're now in, 2040 to 2070, and the dark orange is a factor of 6 increase in the number of heat wave days, factor of 6. Furthermore, under medium to high emissions, many crop yields plummet, as indicated in this graph. At the bottom, global temperature change. At the top, what global temperature means for how much warming there is at low latitudes and how much warming there is at mid to high latitudes, where these different crops are grown, some grown in Africa and India, some grown in the United States and Asia. But interestingly enough, these declines have been estimated without taking into account any increase in major droughts. And when you look at what's likely to happen in droughts, under high emissions, the drought frequency virtually soars. This is the frequency of 4 to 6 month duration droughts. How many events per 30 years are expected? And we're comparing 61 to 90 against 2070 to 2099. The red is, again, a huge increase in the frequency of 4 to 6 month duration droughts, and you look at what happens across much of North America, much of Africa, much of South America, including Amazonia, much of Europe, it really is very striking. Wildfires, even a 2 degrees C increase, a low emission future, portends a large increase in wildfires. We've already seen a large increase at 1 degree C. And you look at these percentages for the western United States as modeled by the National Academy of Sciences, you see percentages 200%, 300%, 400% increases in average annual area burned per degree centigrade increase in the global average surface temperature. Increased storminess. Again, we're seeing increased storminess already, and here are some scientific publication titles, including one. David Romps was my postdoc. Very proud of him for doing this work on lightning strikes. Again, not a pretty picture. This is relatively recent work. This was presented at Princeton in April of last year using Princeton's hurricane model, which is one of the better hurricane models that exist. And what it shows is an increase in landfalling Category 3 to 5 hurricanes in the northeastern United States, even under a mid-range scenario. This is an IPCC mid-range scenario, not the worst ones. Really quite striking. Sea level likely to rise another 1/2 to 2 meters by 2100, depending on the emission scenario. Low emissions give us a better chance at the lower number. High emissions are likely to take us toward the higher number. But what's important is that this graph just goes to 2100. As I mentioned before, by the time the sea level comes to equilibrium, it gets much higher. Sea level rise continues for many centuries after 2100 in all scenarios, reaching typically 2 meters or more per degree of global average warming. And here's what 1 meter does in the northeastern United States. The red are areas that would be flooded with 1 meter of sea level rise. Acidification, we expect continued drop in ocean pH in all scenarios with significant impacts on marine life. I already mentioned what the damage is to organisms that form their shells or their skeletons out of calcium carbonate. That includes corals. And basically what this shows is that under a mid-range scenario, portrayed on the right, the green is conditions conducive to warm water coral survival and growth. The red are conditions inimical to warm water coral survival and growth. And you see that by the middle of this century, we could have lost a considerable fraction of the warm water corals. Now, what else could happen? What I've shown up until now are things that we have very strong reason to expect will happen, where you can make a best scientific estimate. But there are some other possibilities that we can't yet quantify in terms of their probability, their timing, their magnitude. One of them is rapid methane and carbon dioxide release from thawing permafrost and warming Arctic sediments that could accelerate all climate-related impacts. Major focus of the Woods Hole Research Center. Our founding director, George Woodwell, was one of the first to say this could be a really big deal. A lot of people snorted and didn't believe him. We are now measuring increases in these gases coming out of the far northern soils. There's 2 to 3 times as much carbon in the far northern permafrost as is in the atmosphere now. So there's huge potential for making things worse. Massive drying and fires in what I call the formerly moist tropics, with huge damage to local peoples and biodiversity. Another big focus of the Woods Hole Research Center that works both in South American forests and in Africa. Greatly accelerated sea level rise from rapid disintegration of Greenland and Antarctic ice sheets. There are folks who say there's reason to think sea level could go up by multiple meters in this century, even as many as 3 or 4. That's controversial because we don't really understand the mechanisms by which these ice sheets could very rapidly lose ice, but the picture is not getting better with time. As new results come along, they're mostly showing that the possibility of losing these ice sheets very rapidly is larger than we thought before. Ocean fisheries crash caused by a combination of warming, acidification, oxygen depletion, toxics, overfishing. The oceans are really taking a beating. And folks here at Brown know that. Oceans are a major focus of environmental science work here at Brown. And again, it's not a pretty picture. These multiple stresses are very hard to analyze in terms of predicting quantitatively what they will do in combination, but it's not likely to be good. And the last one here, collapse of the Atlantic meridional overturning circulation, the thing that drives the Gulf Stream, which could lead to more extreme winters, particularly in Northern Europe, even in a world that's warming as a whole. And the key point, and one of the things that caused the Paris Accords to introduce 1.5 degrees as an aspirational target, lower than the 2-degree and already very demanding target that had been agreed long before, is that all of these become more likely, according to current understandings, as the change in temperature goes above 1.5 degrees C. So what we should do, I like this Chinese quote, if you don't change direction, you'll end up where you're heading. I wish more of our political leaders understood that. First thing to understand is there's a big difference between the expected harm depending on the action society takes. People talk a lot about the uncertainty in the climate future. They say, well, we don't really trust the models. Our predictions aren't that great. You need to understand that the biggest uncertainty about how much climate change we're going to get is what society decides to do. If we act aggressively to reduce greenhouse gas emissions, we will get much less temperature change than if we don't. The left is one of the low Intergovernmental Panel on Climate Change scenarios. On the right is the high one. And the high emission scenario leads to global average surface temperature increases of 5 degrees C or more. That would entail catastrophic impacts. There's just no doubt about that, even though you can't spell out exactly what all of them will be or how big they will be. We have every reason to believe they'll be catastrophic. So hiding our heads in the sand is not smart. This is a cartoon from my favorite cartoonist, Tom Tolles, with whom I had the great pleasure of having lunch yesterday. He does his cartoons for the Washington Post, but they're syndicated across 200 other papers, and a lot of them are about climate change, which is a passion of his. I like this one a lot. So what can we do? We have really only three options. Mitigation, meaning things we do to reduce the pace and magnitude of the changes in climate being caused by human activities. Adaptation, meaning measures that we take to reduce the impacts on human well-being resulting from the changes that do occur in spite of our best efforts at mitigation. And the third option is suffering. Suffering the adverse impacts and the disruption of society that we fail to avoid by either mitigation or adaptation. And the reality is we're already doing some of each. We're doing some mitigation, we're doing some adaptation, and we're doing some suffering. What's up for grabs, what's at stake, is the future mix of those three. And if we want to minimize the amount of suffering, which of course is what policy is supposed to be about, we can only achieve that by doing both a lot of mitigation and a lot of adaptation. They're not alternatives, they're complements. Mitigation alone won't work because climate's already changing, we can't stop it quickly. Adaptation alone won't work because it gets costlier and less effective the larger the changes in climate to which you're trying to adapt. So we need enough mitigation to avoid unmanageable climate change and enough adaptation to manage unavoidable climate change. A lot of possibilities for mitigation. Certainly we want to reduce the emissions of greenhouse gases and soot, absorbing particles from the energy sector. We want to reduce deforestation, increase reforestation and afforestation. We want to modify agricultural practices to reduce emissions of greenhouse gases and build up soil carbon. And again, these last two are things that the Woods Hole Research Center focuses on very heavily. Conceivably, we might learn to affordably scrub greenhouse gases from the atmosphere technologically, but that's a very long reach. Trees do it much more cheaply. And we might resort in desperation to so-called geoengineering to try to create cooling effects offsetting greenhouse heating. And my own view is that needs to be studied, but it is fraught with peril, and I don't think anybody should count on a big contribution from geoengineering other than painting roads and roofs white instead of dark. That only works to a small extent because only 2 to 3% of the world's surface is covered by roofs or pavement. But that's the simplest form of geoengineering. But the other approaches, things like injecting reflecting particles into the stratosphere, are very tricky indeed. And you have to ask, even if you do that and you get some temperature benefit, what would happen if for one reason or another you suddenly stopped? And then the whole sudden impact of all the greenhouse gases accumulated in the meantime would be felt. How much mitigation, how soon? We've mentioned a couple times the 2 degrees C target. That's not because it's safe. We're at 1 degree and that's not safe, as I've noted. It simply was embraced as the most prudent target that many folks thought still might be achievable when they embraced it initially in the European Union in 2002 and in the G8 and G20 in 2009. As noted, we added an aspirational goal of 1.5 in 2015. To have a 50% chance of staying below 2, we would need to stabilize the atmospheric concentration of heat-trapping substances at around 450 parts per million CO2 equivalent. That means you translate the effects of the non-CO2 substances into forcings and see how much CO2 that's equivalent to. To get there, developed country emissions needed to peak around 2015 and decline rapidly thereafter. Developing country emissions need to peak no later than 2025 and decline rapidly thereafter, and everybody's got to get on board. What this slide is about, I won't take the time to talk about it, but it just shows how widely distributed the emissions are. You can't do this with one silver bullet. In fact, I say this so often that some of my colleagues have come to call me Silver Shotgun Holdren. Because there are a lot of sectors that are important, there are a lot of countries that are important. You really need everybody on board. Can we afford it? Detailed analysis by the McKinsey Group indicated that if you had a carbon tax that increased over time to $70 a ton of carbon dioxide equivalent by 2030, that would put the world on a 2 degree C trajectory, which you then have to continue. You need an encore, of course. The total tax bill would reach $2 trillion in 2030, but that's not actually the cost, because it's the marginal cost. It's the cost to get the last tons of carbon dioxide avoided. The average cost is much less, and the governments that collected the $70 a ton could use the money, a lot of the money, in other ways. They could reduce other taxes, they could do R&D, they could compensate the poor for the otherwise regressive impacts of a carbon tax. And for comparison, gross world product in 2030 at 2.5% year per year growth between now and then would be $170 trillion. That's in purchasing power parity terms. In that case, even the $2 trillion figure, if you counted the whole thing, would be 1% roughly of gross world product. And for comparison, the world now spends 2% of gross world product on defense. The United States spends 3.3 and 1.7% on environmental protection. And furthermore, these costs are not losses, they're just choices about how society allocates its resources. Most economic models do find that aggressive mitigation would reduce gross world product somewhat, maybe 2 to 3% of gross world product in 2100, but most people who study these models believe that they underestimate innovation and that the impact would actually be less. And the key point is that much less affordable would be the cost of unmitigated climate change. That is, it's much cheaper to address it than not to address it. Lots of adaptation possibilities. I won't read you this slide. The key point about the adaptation possibilities is that many are win-win. They'd make sense even if climate were not increasing the frequency and intensity of floods, droughts, heat waves, wildfires. We always had those events in the past. We were always less than fully prepared. The kinds of investments that were proposed in the Obama administration to deal with this would have made sense even if climate were not changing. And let's talk very quickly, I'm almost done, about the need for and current lack of federal leadership. In the Obama administration, we did a lot. We boosted climate research and monitoring. We invested a lot in key energy research and development and incentives. We promulgated aggressive energy efficiency standards. We promoted climate change adaptation, launched the Climate Action Plan in 2013 with the first bullet of things we did in the first term in 2013, launched the Climate Action Plan with further mitigation and adaptation measures, further international initiatives, reached agreement with China that was announced in November 2014 and really made possible the Paris Accords with 195 other countries in December of 2015. The Trump administration, by contrast, has put climate contrarians in charge at OMB, the Office of Management and Budget, at the EPA, at the Department of Interior, at the Department of Energy, and they have left most key science positions unfilled, and they propose deep budget cuts in both climate science and clean energy R&D. They've canceled President Obama's Climate Action Plan and virtually all of his executive orders on adaptation. And of course, they announced the U.S. withdrawal from the Paris Accords. So what should we do? Again, very quickly. Sorry this has gone on too long. States, communities, businesses, and universities should devise and implement their own mitigation and adaptation plans. Many have already been doing that. Scientists should continue to do their work monitoring and analyzing climate change and improving projections, and they should explain to every available audience what we know, how we know it, how it affects that audience, and how we can fix it. Philanthropists should seek to fill the gaps in climate research and education created by federal government cutbacks. Opinion leaders should get better at explaining climate change impacts and remedies and at rebutting contrarian errors. And everybody should be in the business of letting Congress and President Trump know that abdicating U.S. government leadership in this space is nothing less than folly. Individuals can do a lot of things to reduce their own carbon footprint. Get an energy audit of your home, shrink its energy waste, replace your lights with LEDs, light-emitting diodes, put solar cells on your roof, walk, bike, or take public transportation rather than driving. If you are going to be driving, get a hybrid, all-electric, or other high fuel economy car. Recycle and, better yet, reuse. Eat less meat. Meat's a big emitter of greenhouse gases. No time to talk about why, but it is. Invest in companies that are taking action on climate and disinvest in those that aren't. And for the biggest impact available to young people, have one fewer kid. There was a recent study on the things that you could do to have a big influence, and that was the biggest. That was the biggest. Trend is not destiny. Thank you very much.
That was fascinating, if not depressing. So yeah, first of all, I want to thank John for joining us and giving us such a wonderful overview of climate disruption. I think that's a really wonderful way to characterise what we're experiencing at the moment. One of the things that I wanted to add in terms of what individuals can do, and this is something that I always say when students ask me what they can do about climate change, and that is vote. So I would like to add that to your list.
Yes, no, it belongs on the list.
Yeah.
I usually save that for the Q&A.
Yeah. So I think that given the time, I'd like to actually open this up to questions from the audience so we can take advantage of John's time here. Do we have questions? Stephen?
And there are mics in the aisle. You probably should go to a mic. You could even line up behind the mics if you want.
Yeah. Loud mouths like Stephen, I think, can probably
manage.
For sure.
So my question is about the ongoing debate between, say, Mark Jacobson and Stanford and others about whether we have a reasonable way to 100% renewables in the U.S. by 2050. So, some people say, yes, it's doable and only our stupidity is keeping us from doing it. And others say it's just not possible and we're going to continue to need fossil fuels well beyond that. I'm curious what your thoughts are on that trajectory.
I don't have a clear crystal ball. I don't think anybody does. I think it would be extremely challenging to get to 100% renewables by 2050. I think if we could get a significant contribution from nuclear energy as well on that time scale, that would help. Getting that significant contribution requires overcoming a number of hurdles to expanding nuclear energy worldwide. An economic hurdle, it's too expensive. You got to make it cheaper while making it more safe at the same time. You've got to solve the waste problem. You've got to minimize the link between nuclear energy and proliferation of nuclear weapons. But there are also challenges with expanding renewables to a 100% extent. And one of them is having to pay for storage, which you're going to have to do if you go to 100%. The other thing that we may be able to do, if we are sufficiently clever, is continue to burn fossil fuels, but with carbon capture and sequestration away from the atmosphere. And I think we should continue to invest in ways to make that affordable, even if some people say that's a low probability. Because again, if we could figure out how to affordably capture and sequester the carbon dioxide from particularly burning natural gas, which is becoming our big bridge fuel, natural gas in power generation. And if even better, we could burn sustainably grown biofuels in power plants and capture the CO2 from that and sequester it, then we would effectively be sucking CO2 out of the atmosphere, because the sustainably grown biofuels would be carbon neutral, even if when you burn them they put the CO2 back in the atmosphere, because what sustainably grown means is your biofuel operation is sucking as much CO2 out of the atmosphere in the growing plants as the ones you're burning are putting back in. If instead of letting the burning ones put it back in, you grab that and put it in the ground, you actually have a technology for drawing down the carbon dioxide content of the atmosphere. That too is a long shot for many reasons. Just figuring out how to grow that quantity of biofuels without interfering with food production, without interfering with essential ecosystem services, without interfering with forestry production, that's a big challenge. But there is no free lunch in this domain. In fact, another of my favorite sayings is, not only is there no free lunch, but a cheap lunch can give you indigestion. Looking for cheap fixes like, let's just inject a bunch of sulfates into the stratosphere and cut off the cooling, we'd get a very bad case of indigestion out of that, including decimating the stratospheric ozone layer and getting big increases in ultraviolet radiation at Earth's surface, with increases in skin cancer, melanoma, and so on. So there is no free lunch. Every approach has liabilities. One of the reasons we should be drastically increasing and not decreasing our federal investments in clean energy R&D is to minimize the liabilities of each and every potentially attractive energy source, to see if we can make them economically affordable and environmentally tolerable. And we're going in the wrong direction. President Obama, at the beginning of the Paris conference in December 2015, got up with 19 other national leaders, heads of state, and pledged under a program that we called Mission Innovation that all 20 of these countries would double their investments in clean energy R&D over the succeeding 5 years. And this was matched with a program led by Bill Gates, where very rich private individuals agreed to put large chunks of their own money into taking the best ideas that emerged from a rapidly accelerated government program of R&D, in translating that in the private sector into widespread application. Great idea. Wasn't entirely mine, so I can say that. And now President Trump, instead of doubling these investments over 5 years, has proposed that we cut them in half in 1 year. This is the wrong direction. I can tell you one thing for sure. In that direction, we're never going to get to a much higher contribution from renewables, whether it's 100% or 70% or 60% in 2050. We're not going to get there at all if we don't make the investments. We're not going to improve nuclear. We're not going to figure out how to capture and sequester carbon dioxide in an affordable way.
Thank you. We have a question from Professor Head.
Dr. Holdren, I'm really interested in your prognosis about our ability to work with China. I'm a planetary geoscientist, and we've suffered a lot from the Wolf Amendment, which prohibits us from, as you well know, interacting in many ways. My thinking is obviously that if we can work closely with one of the other major areas of concern, that it could benefit us. And I'm just interested in your prognosis, and also if there is no possibility of the U.S. working effectively with them under this administration, what do you think China will be doing alone? I see a lot of evidence when I go there that they're making great strides, but I'm wondering what your prognosis is.
Yeah, it's a great question. Congressman Wolf, who has since retired, actually tried to put me in jail for continuing to work with China.
I asked.
He only failed to put me in jail because he was trying to put me in jail under what's called the Anti-Deficiency Act, which makes it a felony to spend appropriated funds for unauthorized purposes. And he had injected into a 1,000-page appropriations bill a prohibition on either OSTP, my office, or NASA having any interaction whatsoever with any Chinese citizen, never mind with the government. And we disobeyed it on the advice of counsel, who said that if we were to obey that prohibition, we would be surrendering the president's constitutional authority to conduct foreign diplomacy. And so we kept working with China through in the OSTP. NASA didn't because they had a much bigger budget at stake, roughly $18 billion. My budget was $6 million. Chairman Wolf cut it by 32%. When he couldn't put me in jail, he cut my budget by 32%. It was painful, but we kept cooperating with China. Now that's all at risk, of course, because President Trump does not appear to believe in international cooperation in science and technology. Like many members of Congress, he seems to think it's a siphon through which U.S. technical advantage is hosed into the possession of our competitors and potential adversaries. This is a crazy view. I go to China a lot. I went to China a lot before I was in office. I went a lot when I was in office. I'll continue to go a lot now, and you're absolutely right. China is making great strides. They're not doing this because we told them we wanted them to do it. They're doing it because they see it in their national interest. And by the way, it's estimated that the market, the global market for clean energy technologies, efficient energy technologies from now until 2040 is between 25 and $30 trillion. And China will be perfectly happy if they own most of that market and split the rest with Germany and Japan and South Korea. It's terrible business from the U.S. standpoint. I mean, one of the saddest things about President Trump announcing U.S. withdrawal was that a very sizable fraction of leading U.S. CEOs in the business community urged him not to. And then he got up in the Rose Garden and said, this agreement is bad for U.S. business. Absolute crock. The technical term is steaming pile. Anyway, when I say we, my group at Harvard, a lot of other university groups that I'm connected to are continuing engagement with China on technology innovation for deep decarbonization. We're finding funding in the philanthropic and business communities to support this work. We still will not be able to replace everything that the federal government was doing, so it's going to be very challenging.
Thank you very much.
Yeah.
Okay.
Hi, thank you for your talk today. I'm curious, here in the Ocean State, we have a lot of infrastructure that we're fixing. Our bridges, many of them are being fixed and replaced, and we're trying as a state to identify what level of sea level rise we should be planning to build our infrastructure. You know, we build a bridge today, it should hopefully last 60 to 80 years from now. So you shared the number 2 meters or 6.6 feet. That has been the number that we as a state had adopted. There have been conversations about the NOAA 2017 models that came out in last January, that the high rates are more at 9, 10, even up to 11 feet of sea level rise. Given the national conversation on infrastructure, especially transportation infrastructure, how do you recommend we as a state address both those risks and what numbers should we be planning to for sea level rise as we need to make the most of our investments?
Yeah, this is a great question and a very sophisticated question. What we are seeing, Trump has just announced his infrastructure plan, which has many flaws. He says we're going to spend $1.5 trillion on infrastructure, but when you read the fine print, somebody else is going to pay for it. The federal government is going to pay for almost none of it. But in addition, there is no resilience adaptation built in to Trump's view of what rebuilding our infrastructure consists of. This would be an enormous lost opportunity, and it will only be remedied if in whatever infrastructure plan is actually implemented, the cities and states play a major role. And again, one of the reasons for optimism, and there are a few, is that cities and states are stepping up. I mean, we have more than 20 states have signed up in this "we're still in" movement, that the federal government may be out of the Paris Accords, but the states are still in. Hundreds and hundreds of cities have joined this movement, still in. More than 1,000 businesses say they're still in. These non-federal government entities are going to have to step up, as so many have pledged to do, to remedy the deficiencies in the federal government's stance. And a big part of that, without question, is ensuring that as we rebuild U.S. infrastructure, that we take climate change into account. How much sea level? Very tough question. In my opinion, we should be reckoning with at least 6 feet. Just thinking, if you want this infrastructure to last 50 years, you'd better reckon with 6 feet. If you think you're building infrastructure that will last 100 years, you want to be on the safe side, you'd better reckon with 12 feet. That's a personal opinion. Some would say Holdren is crazy, there's no way it's going to go up that much. But that's the direction in which things are moving. As you look at the latest analyses of what is happening in both the Greenland and Antarctic ice sheets, they contain huge amounts of water. The Greenland ice sheet alone contains 23 feet of sea level. The Antarctic ice sheet contains some 200 feet of sea level, more than two. Just the West Antarctic ice sheet contains about 18 feet of sea level, and it's the most vulnerable. So again, a lot of uncertainty about how rapidly those ice sheets could disintegrate, but a prudent strategy, and we should be in the business of prudent strategies. A strategy that would save a lot of money in the long run is to count on the higher end of the projections when you build new infrastructure.
I think I should also add that certainly in Rhode Island, we feel this, and I know that it's true across the US, that universities feel a strong obligation to support state and local government to help make those decisions. So we have time just for one last quick question, and then we'll need to break up. So you're the lucky one.
Okay. Hello. Thank you for your talk. I learned a lot. I am an international student, and when I came to the US, I've never seen such a culture with excessive consumerism and indulgent. And my question goes on a more micro level. Despite all the conversation, all the facts and statistics, there seems to be a bridge between action and understanding. People understand a lot of what's going on, but how do you have a suggestion to how you bridge that gap to actually people eating less meat, people less traveling on plane, people change their choices with Prime, Amazon 2-day purchase? What is your opinion on that? Thank you.
My opinion is that this is a glass that is both half empty and half full. That is, there's all kinds of rampant consumerism that is contributing to the problem and that is not actually generating much increase in real well-being. It's not actually making people happier. They do it because everybody else is doing it. On the other hand, there's a lot of change going on. If you look in certain communities around the country, the number of Priuses is outnumbering practically everything else, including in the Woods Hole Research Center parking lot. If you look at the number of buildings that have solar cells on the roof or wind turbines in the front, as the Woods Hole Research Center does, those numbers are increasing drastically. If you look at the number of people who are recycling, if you look at movements like one my 12-year-old granddaughter helped launch in Woods Hole, Skip the Straw, keep the plastic pollution out of the ocean. These are the half-full part of the glass. These are the encouraging things that are happening. One of the other things that's encouraging but discouraging at the same time is that about 70% of the American people believe climate change is real, humans are causing it, and we need to do something about it. But when you ask them what keeps you awake at night, what worries you most, it only ranks like number 15. And we've got to get it to the top 3 before people start voting, and here's my issue, before people start voting on the basis of that issue. We need people to vote on the basis of that issue. Encouraging sign, thousands of scientists and engineers have decided to run for office at local, state, and national level in the 2018 election, far more than ever ran before, because they're so discouraged by what has happened in terms of lack of respect for evidence, lack of respect for facts. So things are changing. They're not changing fast enough, and we need to figure out how to get that 70% who already believe climate change is real to increase the priority they place on it. And that's one of the things that that I hope I'm contributing to by explaining that climate change is moving faster than most people think. It's already doing more damage than most people think. This is not just a problem for our grandchildren. If we don't get going now, we're going to be cooked, literally. And with that happy note.
Yes. And on that note, thank you very much.
There's a reception outside, so we can continue this conversation in a more informal setting.